The role of artificial gravity in long-duration space missions is a critical aspect of space travel research, addressing many of the physiological issues astronauts face in microgravity environments. Extended exposure to microgravity results in various health problems, including muscle atrophy, bone density loss, fluid redistribution, and changes in cardiovascular function. Artificial gravity could potentially mitigate these effects, providing a simulated gravitational force that mimics Earth's gravity, thereby preserving astronaut health and functionality during long-term missions, such as those to Mars or deep space habitats. Physiological benefits. One of the most significant benefits of artificial gravity is its potential to counteract the musculoskeletal deconditioning that occurs in microgravity. On Earth, gravity forces muscles and bones to maintain strength and density through daily activities. In space, the lack of this natural stimulus leads to rapid muscle wasting and bone demineralization. Artificial gravity could stimulate these systems continuously or periodically, reducing or even preventing these health issues. Similarly, the cardiovascular system also suffers in microgravity, as blood shifts towards the upper body and head, leading to vascular adaptations that impair its function post-mission. Artificial gravity would help maintain normal fluid distribution and cardiovascular function, mimicking the conditions on Earth and enabling astronauts to stay healthier and recover faster upon return. Technological approaches. Several methods have been proposed to create artificial gravity in space. The most discussed is the centrifugal force method, where a spacecraft or a section of it rotates to generate a force akin to gravity along the outer edge. This can be achieved in various configurations, from a rotating wheel space station, similar to what was depicted in the movie 2001, A Space Odyssey, to smaller centrifuge devices within a spacecraft where astronauts could spend several hours a day to maintain physical health. Another less developed but potentially promising approach involves linear acceleration, where alternating acceleration and deceleration could create a sensation of gravity. However, this method poses significant challenges in terms of spacecraft design and fuel consumption, making it less feasible with current technology. Psychological effects. The psychological benefits of artificial gravity are equally important. The disorientation and nausea experienced by many astronauts in microgravity could be alleviated with the introduction of a gravity-like force. Moreover, having a defined up and down could create a more intuitive and comfortable living and working environment, reducing stress and potentially improving overall mental health. Research and experiments. Current research into artificial gravity is mostly confined to ground-based studies and short-duration experiments aboard spacecraft. Human centrifuges on Earth, for example, have provided valuable data on tolerance levels and potential health benefits. In space, experiments like NASA's artificial gravity pilot study aboard the Space Shuttle have tested short-term human responses to artificial gravity. Moving forward, more extensive testing in space will be necessary to understand the long-term effects and feasibility of different artificial gravity systems. Proposals for dedicated artificial gravity research facilities, such as those in the conceptual planning stages for inclusion on the Lunar Gateway or other deep space habitats, underscore the importance of this research. Design challenges and considerations. Implementing artificial gravity on spacecraft introduces several design challenges. The structure must withstand the stresses of rotation, and systems need to be developed to transition safely between zero-gravity and artificial gravity environments. Additionally, the impact of partial versus full Earth gravity needs to be studied to determine the optimal level of artificial gravity required to counteract the adverse effects of weightlessness. The size and scale of artificial gravity facilities also pose logistical and cost challenges. Larger structures that can provide near-Earth gravity conditions require significant materials and propulsion capabilities, which currently exceed budgetary limitations for most space agencies. Future implications. The development of effective artificial gravity systems is crucial for the future of human space exploration. As missions become longer and aim further into our solar system, the ability to provide a livable environment for astronauts will be key to their success. Artificial gravity not only holds the promise of enhancing astronaut health but also the overall viability of living and working in space for extended periods. In conclusion, while the implementation of artificial gravity in space missions presents significant engineering, medical, and financial challenges, its potential benefits to astronaut health and mission success make it an essential area of research. As technology advances, The prospects of integrating artificial three-dimensional vector representation, where each color corresponds to a dimension, can be particularly effective in distinguishing multidimensional clusters.